Tolong ambilin kertas tuh.
Assalamualaikum.
Waalaikumsalam, Ibu.
Oke.
Selamat siang Bu Tuti.
Iya, halo cantik. Where are you now?
Just at home now.
Di Jakarta?
Yes, Bu, masih di Jakarta.
Masih di Jakarta.
Hi.
So, good afternoon, Professor Black.
Good afternoon. Good morning. No, it's still afternoon for you.
So, good afternoon, Professor Hayashi. Good morning, Professor Commeiras.
Yeah. Hi, this is Hayashi. Thank you very much.
Thank you very much for your attending.
Thank you.
Konnichiwa.
Konnichiwa.
Genki desu ka?
Yeah, thank you very much. Yes,
Hayashi.
well, you can speak Japanese very good.
No, just a bit.
Hello, Professor Black.
Hello,
Professor
Kodik. Hello.
Commeiras. How are you?
I'm well, thank you.
Wow, that's great. That's nice to see you now, even though.
We're in lockdown still.
Yes. So how's Sydney?
Maybe another couple of weeks and we'll be allowed out. But
Okay.
it's very hard to get into the university.
Yes.
We have limits, restrictions on the number of people.
Yes. We do the same things, I think, in Indonesia.
So it's more important that the real people go in. Each group is allowed 9 people.
Hello, good day, everyone.
Hello.
Hello, Pak Roto.
Hi, Pak Roto.
I hope that you are going good.
How's
So,
undergoing, Prof. Black?
you have 33 people
Yes, we have.
participating.
Yeah. So we have 171 who registered for this event today.
71, okay.
That's
that's
good.
great.
That's good number.
171.
That's good
see.
number.
Yeah, let's see. Okay.
So who will speak today?
So today we will have 2 lectures. Yeah, the first one will be delivered by Professor Black, and the second one will be delivered by Professor Hayashi.
Hayashi.
Yes. Professor Commeiras, can you hear me?
Pak Roto kok pakai itu backgroundnya?
Belum tak ganti ya, mohon maaf.
Yes,
I
please.
have to check. Sorry.
Yes, because you have to get for the speech.
Yeah.
I think.
This is my previous meeting background. Sorry, I have downloaded actually the visual background I got from Pak Idham actually. I downloaded it yesterday. It was. I guess this one.
Yes.
Yeah.
Thank you.
Yeah.
I don't know how to put the background. Can you do that, or
you can
tell me
download
what I have to do?
You can download the file that I have sent you yesterday, and then you go to the Zoom. Take a look at the bottom left, and then you will see the video in here. So I think that share screen.
Hi, Mentari, are you there? Hi, nice to see you. Halo, Ibu. Hi, everyone.
Hey, Mentari.
Hai Mentari.
Are you
Everyone just meeting in here.
Oh yeah.
Oh, it's good to see you.
So we have some homecoming student here.
Such a small reunion.
Yeah.
Small reunion,
Homecoming
right.
I guess we should have some kind of meeting after the COVID ending.
Yeah, we should.
Mentari, where are you now?
I'm in Mataram, Pak,
Oh,
actually.
Mataram.
I've been here
Okay.
for a month now.
Oh,
Yeah.
okay. Yeah.
In where? At what?
Mataram.
Lombok.
Mataram.
What are you doing there? I am now working for an NGO for
Oh,
SID
NGO. Yeah.
for development. Yes. Okay. Lovely. I miss chemistry though. That's why I'm here with you guys. Yes. Joining
Is that
with
the
Prof, right?
is that the NGO nothing to do with chemistry or what?
No, we are, but we're mostly focused on public health, right? For maternal and
Okay,
child development.
Is it completely separated from chemistry or still have some intersection or something?
A little bit, mostly public health. It's more about nutrition, and we're now focused on COVID and pregnancy. So.
Wow, that's quite challenging then. Yeah, whatever you do, actually, we would like to hear. As long as you love it and you you enjoy it.
Enjoy doing it.
Yeah.
Okay, I think that we may start in 1 minute.
Yeah, it's about the time, right?
Yes. Safi?
Should we start now? Because it's already 1 p.m.
Yeah, we can start in 1 p.m. and 5.
5 minutes past the
All
hour.
right.
1 more minute.
Yeah, 1 minute.
Pakai anu aja, pakai. Okay, Mbak Safi, you can start.
Okay, so perhaps before we start, I would like to read to you the rules for guest lecture for today. First of all, participants must have their real names, not pseudonames or calls, by following the format participant_name, moderator_name, host or committee_name, speaker_name. Second of all, participants, please wait for approval from the host in order to enter the meeting room. Third of all, when entering the Zoom meeting, participants and related parties are not allowed to turn on the audio before being invited by the moderator and can be turned off directly by the host if it is deemed quiet, disturbing. Fourth of all, when entering a Zoom meeting, participants and related parties must turn on the video. It is allowed to turn off the video if there are signal or network problems or it interferes with the smooth use of the Zoom meeting. Fifth of all, participants can use the chat room to interact with fellow participants for the needs of the event by using polite and courteous language. Six, participants are not allowed to say rude and disrespectful things. Seventh, participants must follow the applicable rules. So all participants, please refer to the link sent in our chat box for attendance record. So let's begin. Good afternoon, everybody. To the honorable invited world-class speaker, Professor Laurent Commeiras from Aix-Marseille University, France. To the honorable speakers, Professor David Black from the University of New South Wales, Australia, and Professor Yujiro Hayashi from Tohoku University, Japan. To the honorable Head of Chemistry Department, Universitas Gadjah Mada, Indonesia, Dr. Otto. To the honorable host of World Class Professor Program 2021, Dr. Idham Darussalam from Universitas Gadjah Mada. To all amazing lecturers from Universitas Gadjah Mada and all participants. Welcome to the very first session of online guest lecture of World Class Professor 2021. On this occasion, we are raising the topic of green chemistry approaches for efficient synthesis of heterocyclic compounds. Thank you all for attending. My name is Safi, your master of ceremony and moderator of the day. It is my greatest honor to assist you through today's lecture. First of all, let us all deliver our thanks to God for all his blessings that we are able to attend today's event with good health and happiness. It has never ceased to amaze me how impactful technology has been for us, that despite the ongoing pandemic out there, we are still able to enrich our knowledge from a fruitful lecture by amazing professors that come from all around the world through an online setting. Before we begin our first lecture of the day, I'm going to briefly read to you the rundown of today's session. Firstly, we are going to listen to a few opening remarks from Dr. Otto, Professor Laurent Commeiras, and Dr. Idham Darussalam. Afterwards, we will begin today's lecture by Professor David Black from the University of New South Wales, Australia, as well as Professor Yujiro Hayashi from Tohoku University, Japan. And lastly, to close today's event, there will be a closing speech from Dr. Idham Darussalam. Now, without further ado, we will proceed to our first agenda. Dr. Otto, as the head of Chemistry Department, Universitas Gadjah Mada, will be giving his opening remarks. Dr. Otto, the time is yours.
Thank you very much, DM. Assalamualaikum warahmatullahi wabarakatuh. Dear esteemed professor, guests, ladies and gentlemen, as the head of the Department of Chemistry, Gadjah Mada University, wish to welcome you all, especially Professor David Black and Professor Yujiro Hayashi and Professor Laurent Commeiras, who have been in touch so far with our colleagues, our lecturer, Dr. Idham Darussalam, and to join this today's opening world-class professor lectures. As a community of chemistry, we are bound to save the future of chemistry through research and publication. Research usually starts with a good research problem, developing hypotheses, execute the lab work, and writing the papers. Chemistry must be developed to tackle the current and future problems. I believe that all the invited lecturers today are capable of lead us to be a leader of tomorrow in chemistry. Chemistry may need to be increasing interdisciplinary like before, and there could be a significant shift from blue skies to problem-driven research. There is a risk, however, that chemistry, or I'm afraid that chemistry will be turning into the follower discipline in the discovery, which is we are not satisfied with that. And also likely that chemistry science will be increasingly required to solve challenging, especially in energy and climate problems, food production, and also clean water. Chemistry might have been increased role in biochemistry and pharmaceutical industry, as well as maintenance and development of infrastructure. And as you know, that there is maybe a global growth in demand for chemical sciences, which might be not necessarily a result of significant shift of chemistry to low-cost economies. It might be challenging for us in the world to remain the top-tier leading chemists across the globe. So we are happy to have Professor Black, Professor Yujiro Hayashi, Professor Laurent Commeiras, which will lead us as a good example of the leader in research and publication in chemistry. Thank you very much and have a successful lecture. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Otto, for the wonderful speech. Next, we will hear an opening remarks from our invited world-class speaker, Professor Laurent Commeiras from Aix-Marseille University. Professor, the time is yours.
Okay, thank you very much. Mr. the Dean, Mr. the Head of the Department of Chemistry, dear speakers, dear distinguished scientists, dear students, ladies and gentlemen, and dear colleagues, good afternoon. I hope that you and your family are healthy, happily. It is my great pleasure to be with you today, and actually for the 2 months as part of the world-class professor program of the Ministry of Research, Technology and Higher Education of the Republic of Indonesia. Unfortunately, due to the COVID-19 pandemic, the program will be online. So we don't have the privilege and the honor to be together at UGM or Jakarta. However, we try to interact as best we can in order to accomplish our different program activity. Today, it is a part of, today it is the start of the cycle of seminars, conferences with very distinguished professors and researchers. The topic of green chemistry and heterocyclic compounds. I would like to warmly thank Idham as well as UGM University for this event and for this kind of invitation. I hope you will enjoy this lecture and we have a great discussion with a lot of questions. I wish a good success to this symposium and I wish you a good day. Thank you.
Thank you very much, Professor Laurent, for the amazing speech. Next opening speech will be delivered by Dr. Idham Darussalam as the host of this program. Dr. Idham Darussalam, the time is yours.
Okay, thank you, Mbak Safi, for your time. Yeah. So, Honorable, the Head of Department of Chemistry, Universitas Gadjah Mada, Pak Roto. Kemudian, Honorable, the invited world-class professor, Professor Laurent Commeiras from Aix-Marseille University. Honorable, the speakers of today, we have Professor Black from the University of New South Wales, Australia, and also Professor Yujiro Hayashi from the Tohoku University, Japan. Honorable participant, researchers, students, and also distinguished ladies and gentlemen. So, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, bonjour, konnichiwa, ya, Om Swastiastu, Nama Budaya, Salam Kebajikan. Yeah, I hope that you are all doing well. Yeah. First of all, let us praise to the God because of His blessing. We can attend in this opportunity in this meeting, yeah, to have a guest lecture. So before we start, yeah, allow me to introduce you, to show you about our world-class professor program, what it is, yeah, and what will we have in this program, yeah. So. So, World-Class Professor Program is an annual program, yeah, conducted or organized by the General Directorate of Higher Education from the Ministry of Education, Culture, Research and Technology, Republic of Indonesia. So, in this year, here, Professor Laurent and I are organized a world-class professor program, yeah, with the theme of the green chemistry approaches for the efficient synthesis of nitrogen heterocyclic compound. Yeah, so. The invited world-class professor, he is a Professor Dr. Laurent Commeiras from the Aix-Marseille University in France. Yeah. And the host of this program is me, yaitu Dr. Idham Darussalam from Universitas Gadjah Mada, Indonesia. So the objective of this event, yeah, at least we would like to improve and strengthen, yeah, the international network through world-class professor program between Universitas Gadjah Mada and also reputable universities abroad. Yeah, for example, Aix-Marseille University in France. Yeah, and then we'd like to improve the research quality, especially in the field of organic chemistry. So the theme of today is about the organic chemistry, and then we'd like also to increase the capacity, yeah, and the skills of the UGM academic community, and also to improve the quality and the quantity of the scientific publication from UGM researchers. And the main goals, yeah, the main objective is to increase the ranking of Universitas Gadjah Mada in the World University rank. Yeah, in order to achieve this objective, yeah, we would like to perform 2 activities in this world-class professor program. The first one is the fine-tuning publication, and the second one is the guest lecture that we have today. So this is the schedule of our program. Yeah, so far we have conducted 6 sessions of fine-tuning publication last month. Yeah, and we will also have the 7th fine-tuning publication next week. Yeah, and now we have the guest lecture, the first guest lecture, and for the guest lecture we will have 4 sessions of the guest lecture. So you can save the date, yeah, and add the schedule to your calendar if you want. Yeah. So okay. For the fine-tuning publication, here we have the speaker. For example, in here we have Professor Commeiras and also me, and also Ibu Heni Herawati from Universitas Darussalam, Indonesia. And here we have 15 draft of publication to be improved the quality, yeah, about the publication. And for the guest lecture, we have 4 sessions of guest lecture. Okay, so this is the poster of the guest lecture series. Yeah, you can save the date. The first one, yeah, today, the 1st October. The second one, 29th of October, and the third one, 12th of November, and the last one, 19th of November. Yeah. So this is the speakers that we have. Yeah. Today, it is our great pleasure to have speakers. The first one is Professor Black from University of New South Wales, Australia. And the second one, we will have Professor Yujiro Hayashi from Tohoku University, Japan. For the second guest lecture, we will have Professor Melati Hairudin from Universitas Malaysia. We also have Professor Diwan Rawat from University of Delhi, India. And we have Professor Patel from Sardar Patel University, India. The third guest lecture will be conducted at 12 November 2021. Yeah, we have Professor Commeiras from Aix-Marseille University, France, Professor Crafotto from Università degli Studi di Torino, Italy, and then we also have Professor Terhaye from Université Savoie-Mont-Blanc in France. Yeah, and the fourth guest lecture, yeah, 19 November 2021, we also have Professor Commeiras as the speaker. And we have Professor Banik from Prince Muhammad bin Fahd University, Saudi Arabia, and Dr. Palermo, Universidad Nacional de La Plata, Argentina. Yeah. So for the participant, yeah, we have the students, researcher, lecturer, also teacher from the senior high schools, and also the employee, yeah, coming from university in Indonesia, and we also have from the research institute, senior high schools, and also industry and non-government organization coming from Indonesia, Japan, Nigeria, China, Pakistan, and Thailand. So before we start, please allow me to introduce our invited professor today. So the invited professor is Professor Laurent Commeiras. So he is a professor in chemistry, yeah, in Aix-Marseille University. Yeah, and then now, yeah, he is a headmaster of chemistry from Aix-Marseille University. Yeah, he's in charge with the master of chemistry, and then his research of interest is development of new methodologies, including the formation of polycyclic complex structure, and also total synthesis of natural products and the molecule of interest. So, without further ado, yeah, let's start the world-class professor program. Yeah, I hope that you will enjoy, yeah, this discussion, this guest lecture, and we are looking forward to meeting you in this guest lecture. Last but not least, terima kasih and merci beaucoup. Thank you.
Thank you very much, Dr. Idham, for your thorough explanation of this program. Perhaps before we proceed to the lecture, we are going to have a photo session. So please turn on your camera for this session.
Pak Roto kurang naik kayaknya. Nah, a bit, yes.
Okay. That, I think we got it. Do we got it? I'm sorry for the organizer. Please let me know if you.
Just a moment.
Okay.
Capture. There is a 5 screen in here.
Okay.
So the first one. Okay. Second. And third. Okay, that's all.
Okay, thank you very much. So with the end of all opening remarks, we will now start today's lecture. Each lecture consists of 30 to 40 minutes presentation, followed by a 10-minute open discussion. So in this event, we highly encourage you to have an active discussion and ask questions regarding the addressed topic. For participants attending via Zoom, you may ask questions using the raise hand function or through the chat room, which I'm going to read off after the end of the presentation. Meanwhile, for participants attending via YouTube, you may state your question through the comment section instead. I would also like to emphasize that questions in Bahasa Indonesia is allowed, as I'll be glad to help you translate to our honorable speakers. So please do not let the language barrier prevent you from learning. Okay, we are now heading to our first speaker. Our first speaker is Professor David Black. He is the appointed emeritus professor from the University of New South Wales, Australia since 2017. He has dedicated his work on the topic of synthetic organic chemistry, including new methods of synthesis, heterocyclic chemistry, coordination chemistry, and natural product. He has made so many impeccable contributions to the chemistry field through his hundreds and hundreds of publications. He's also the co-author of Organometallics in Organic Synthesis together with Professor Swan. He has so many accomplishments that I cannot even mention one by one. He's the director of Sustainable Energy Initiative in 2019 and a former elected fellow of the Royal Society of NSW. He was awarded with David Craig Medal of the Australian Academy of Science in 2017. Professor David Black will be talking about the introduction of green chemistry. Now let's give a warm welcome to Professor David Black. Professor, the time is yours.
Thank you very much, Savati, for the warm welcome. I think Dr. Idham has got to share his screen and run that. He is more technological than I am. What I plan to do today is to give a very simple background talk because I'm old enough to have been around when green chemistry was invented and the main action started in the late part of the last century. And so what I plan to do is to give a very general background talk that is broader than just the synthesis of heterocyclic nitrogen compounds, but the implications are all there for heterocyclic nitrogen compounds. And I hope this serves as an introduction, and then you can have serious organic chemistry from Professor Hayashi following this. So could I have the next slide, please? The general definition of green chemistry is the invention, design, and application of chemical products and processes to reduce or to eliminate the use and generation of hazardous substances. Next, please. When we come to consider synthesis, the then we can narrow that definition down to the design of new synthetic pathways to perform chemical processes in a very controlled way. So the emphasis here is on control, because if we can control reactions, we can then reduce drastically, or if we are lucky, eliminate completely all the negative environmental impact. Next, please. Now, the ideas behind green chemistry really relate to risk. The main thing is avoiding risk. And while we want to make something, we have a synthetic plan, we want to make a molecule, we want to do something like that, and we usually focus on what we are planning to achieve. But it's very important to consider the complete process, and the complete process involves the consideration of all materials, everything that's involved. And we are then in a situation where we have to minimize the negative impacts and optimize the process efficiency. And so if you consider all the intrinsic hazards of the substances involved, you have a simple formula that says the risk is a function of the hazard and its exposure. So it's a combination between the hazard and the exposure. And previously, most of the risk reduction has been focused on limiting exposure. What green chemistry does is it focuses on limiting the hazards. That's an important thought process change. And if we can limit the hazards, then we have a greater chance of reducing the risk than we have just by limiting the exposure. It's a combination of both. Next, please. And so what green chemistry puts together, it's a combination of regulation, control, cleanup, and remediation. The key here is control. It's all about controlling the reaction process. And if we can achieve that, then what we generate is an economic impact. So the real benefit of green chemistry really relates to industrial chemistry and industrial processes. If you're doing small-scale organic synthesis, for example, in a laboratory, then you can manage to use complicated reagents and complicated techniques, provided the scale is small. But you can't do this if you're working in industry, if you're generating a commercial product, for example, in the pharmaceutical industry. And you have in these industries very clever chemists working in the research laboratories, designing and synthesizing new molecules, which are commercially important. When it is decided that a molecule is commercially important, it's sent off to the process laboratories, and it's the process chemists who are even more brilliant. They are the most brilliant organic chemists around. The process chemists who look at a molecular structure and they look at the synthesis, and their job is to make kilograms of this material essentially for nothing, minimum cost, and without any environmental waste or negative impacts. And that really is where green chemistry is important, because that's it's an economic, commercial impact at the industrial level. But that doesn't mean that you can't use it in the research laboratory as well. And if you can generate green chemical processes that help you gain more efficient syntheses of molecules, then that's a start to the process chemists. Next, please. So there are a range of general principles behind green chemistry, and these are, as I said before, these are more broadly based than just the synthesis of heterocyclic compounds. They're fairly obvious, but these were put together by Paul Anastas and John Warner, who really were the initiators of the green chemistry program. So it is better to prevent waste than treat or clean up waste after it is formed. And synthetic methods should be designed to maximize the incorporation of all materials used in the process into the final products. So a simple chemical picture here is that if you're doing an addition reaction, you're better off than if you're doing a substitution reaction where you have byproducts that you don't want. Wherever practicable, the synthetic methodology should be designed to use and generate substances that possess little or no toxicity to human health and to the environment. Chemical products should be designed to preserve efficacy of function while reducing toxicity. The use of auxiliary substances, solvents, separating agents, for example, should be made unnecessary wherever possible and innocuous when used. There are a lot of people who spend a lot of time trying to design synthetic routes that don't require fancy solvents, fancy separating agents, and protecting groups. That's coming up as well. Energy requirements should be recognized for their environmental and their economic impacts, and these should be minimized. Synthetic methods should be conducted at ambient temperature and pressure. Next, please. A raw material or feedstock should be renewable rather than depleting wherever technically possible and economically practical. The unnecessary derivatization using blocking groups, protecting groups, requiring deprotection, temporary modification of physical chemical processes, these should be avoided whenever possible. Catalytic reagents, as selective as possible, are superior to stoichiometric reagents. So we'll hear a bit about catalysis later on. Chemical products should be designed so that at the end of their function, they do not persist in the environment and they do break down into innocuous degradation products. Analytical methodologies need to be further developed to allow for real-time in-processing, monitoring and control prior to the formation of hazardous substances. If you can monitor a reaction as it's proceeding, then this gives you greater control. Substances and the form of a substance used in the chemical process should be chosen so as to minimize the potential for chemical accidents, including releases, explosions, and fires. Next slide, please. These are all fairly obvious, but they've been summarized down into the 12 general principles by Anastas and Warner. And these are the 12 general principles of green chemistry. First of all, prevention is better than treatment. It's better to maximize the incorporation of all materials into the final product. Use and generate substances that possess little or no toxicity. Products should preserve efficacy of function with reduced toxicity. It's better to avoid the use of auxiliary substances, solvents, and separating agents. Energy requirements should be minimized, and we should, where possible, use ambient temperature and pressure. We should try and use renewable raw materials or feedstocks and avoid derivatization, blocking groups, protecting groups, deprotection requirements. Catalytic reagents are superior to stoichiometric reagents. Chemical products should not persist in the environment at the end of their function. And analytical methodology should allow in-processing monitoring and control. And finally, processes should minimize the potential for chemical accidents. So they're all fairly obvious, and you can have the next slide, please. But it's important to have in your mind, when you're doing synthesis, these general fundamental principles. Now, you might come across some of the early concepts that were involved. Sheldon invented the E factor, where E can stand for environment or for energy. It doesn't really matter. It's a fairly obvious thing. But the E factor was defined as the number of kilograms of waste per kilogram of product. And so you want to achieve a small E factor, a low number rather than a big number, where the kilograms of waste are small compared with the kilograms of product. Barry Trost invented the concept of atom economy, where you consider the ratio of the molecular weight of the target molecule to the sum total of molecular weights of all the substances produced in the stoichiometric equation for the reaction involved. And so this is a matter of controlling as much of the starting material into the product as you possibly can. Next, please. Next slide, please. Then there's the environmental quotient, which is the E factor multiplied by an arbitrarily assigned unfriendliness quotient. This is a very sloppy measurement because it's a subjective feeling about how bad or how unfriendly the environmental impact will be. And you then multiply that by the E, the environmental factor. But people have come up with this. PAC, I should mention in the references, Pure and Applied Chemistry, which is the journal of the International Union of Pure and Applied Chemistry. Then there's the life cycle assessment, which consideration of all the stages along the life cycle of a chemical, as well as the consideration of environmental impacts caused by byproducts and auxiliaries. Next slide, please. Now, these are some specially identified areas for development as far as green chemistry is concerned. One is the use of alternative feedstocks, which can be renewable and less toxic. The use of innocuous or benign reagents. The employment of natural processes for efficiency and selectivity. The use of alternative solvents. The design of safer chemicals. The alternative reaction conditions for efficiency and selectivity, and the minimization of energy consumption. So these I'll consider now with some examples and hopefully illustrate most of these aspects. Next, please. When it comes to alternative feedstocks, there's an advantage here that they are both renewable rather than depleting, and they're less toxic to human health and the environment. The selection of the starting material in a synthetic process is crucial. This considers not only the characteristics of the material, but also its origins and mode of use. The question of whether the material is hazardous or not. You have to consider that at the start. And is the material obtained from a hazardous source, or does it come from a benign source? Does its use require the involvement of hazardous substances or processes? Is the source renewable or depleting? For example, you can have carbohydrates, proteins, fatty acids, and fatty oils, as opposed to fossil and mineral raw materials, which are depleting. Does the source make use of waste material? That's a positive aspect if it can be achieved. Next, please. So when it comes to alternative feedstocks, natural products such as carbohydrates and proteins, fatty acids, vegetable oils and fats, we have some examples here of surfactants, which are used for shampoos and similar things. The first being if you have alkyl polyglycosides, which can be made from glucose and palm oil or coconut oil. Or you might have cocoa monoglyceride sulfates, again, surfactants, which are made from glycerol and coconut oil. Next, please. When we consider innocuous or benign reagents, the use of reagents that are inherently less hazardous and catalytic where feasible. Selection of a reagent requires a similar full analysis. You have to think about all these ramifications of the various aspects that play a part in any synthetic process. Is the reagent hazardous? Can an alternative, more innocuous one be used? Does the reagent give a high conversion and high selectivity? Can it possibly be done with a catalyst rather than stoichiometric reaction? Can we make use of UV light or sunlight? Very cheap and efficient sources. Can a clean free radical reaction be used? Can a natural process be used? Biocatalysis, and we'll see some examples of that coming up as well. Next, please. In the consideration of benign reagents, one of the catalytic synthetic pathways that has received a lot of attention relates to oxidation processes. And here, for example, is the oxidation, the epoxidation of alpha-pinene. And the example is shown there at the top. The essential oxidant is oxygen, but the metal complex catalyst that is used is most notably the one of Jacobson on the left of the screen, which is a manganese chlorocomplex designed from salicylaldehyde or a derivative of salicylaldehyde with a chiral diamine. And you have a situation then that gives you a very effective enantioselective process that gives you one isomer of the epoxide. The oxygen is being delivered from the less hindered side of that molecule. So it's delivered from the side that just has the CH2 bridge rather than the C-dimethyl bridge at the top. Now, we have done some work, and it was done by a good Indonesian chemist, Hayat Sholihin from ITB, who did a PhD at UNSW some years ago. And we expanded from the salicylaldehyde derivative to make use of an indole 7 aldehyde structure. And so on the right-hand part there, you see the similar system is the same in that we made a diamino manganese chlorocomplex from a chiral diamine. It has the advantage that with these reactive indoles, you can close the ring at the top with the methylene bridge. And it turned out that these compounds that we made were very highly catalytic, much more active catalysts than the Jacobson ones. But the price you pay for a more reactive catalyst is that you get a faster, more efficient reaction and you lose selectivity. So with a Jacobson catalyst, you get 99% EE, and the best we could get with ours was something of the order of 35% EE. So while the catalyst is more effective, it was a bit of a sledgehammer, and it didn't give the capacity for selectivity, which is important. Now, these catalysts can be embedded in zeolites, and Wolfgang Hölderich and his group in Germany have done a lot of work on industrial processes where embedding the catalysts into zeolites is crucially important. Next, please. Next slide, please. Right. Benign reagents, again, it's great if you can use photochemical processes. And you have here an example of a conjugate alkylation electrophilic alkenes designed by Albini in Italy. It's a remarkable process because you're taking a maleic ester and toluene and essentially removing two hydrogens and putting a benzyl group. And it's an inconceivable reaction unless you can do something very clever. And here the process involves a photochemical process activated by dicyanonaphthalene. And this takes place, it's a good example of atom economy because most of the starting materials are incorporated in the product. So that's a very important process. It's not, in that case, delivering you a heterocyclic nitrogen compound, but it can be used in similar ways if you have that kind of structural fragment available. Next, please. One of my favorite quotations is from Giacomo Shamchan. It's unbelievable. In 1912, he made this wonderful statement: on the arid lands, there will spring up industrial colonies without smoke and without smokestacks. Forests of glass tubes will extend over the plants, and glass buildings will rise everywhere. Inside of these will take place the photochemical processes that hitherto have been the guarded secret of the plants, but that will have been mastered by human industry, which will know how to make them bear even more abundant fruit than nature. For nature is not in a hurry, but mankind is. It's a wonderfully foresighted observation made many years ago, and now it's coming into fruition through the use of green chemistry. Next slide, please. Now, again, on the process of benign reagents, sometimes you can get away with using free radical processes. These are often very complicated processes, and they often lead to very complex mixtures. But here is a very clever example that uses tetrathiophulvalene, and this mediates a radical process. It generates the radical cation, and that then flows on to produce a carbon radical, loss of nitrogen from the diazonium compound, and the radical ring closure puts together the carbon-carbon link at the right in that structure. And then it moves on to give you a carbon radical, which is picked up and trapped by the water to give you the OH group in the product. And that quite remarkable process was used in the synthesis of aspartospermidine, a very important indole alkaloid. Next slide, please. Now, in the use and employment of natural processes, we can use biosynthesis, biotech-based chemical transformations, which give greater efficiency and selectivity. The use of enzymic reactions, biocatalysis, and these usually give extremely high efficiency and selectivity. They're usually carried out in water at ambient temperature and pressure, and they don't require any protection or deprotection of functional groups. They're often shorter reaction sequences with fewer steps, and they can remove the need for organic solvents, such as dichloromethane. Next slide, please. And some important fermentation products, vitamin B12, I haven't drawn the structure there because it's too big, but that's a good heterocyclic nitrogen-containing compound. The second one there is indigo, also a good nitrogen heterocycle. The third is simple catechol, but these are all produced very effectively by fermentation processes, which are very, very efficient. And then the following three structures at the bottom, these are some important biotransformation products that serve as very useful starting materials. So the first, from naphthalene, you can dihydroxylate that quite selectively to get cis dialcohol. Then we have the pyrimidine carboxylic acid and acrylamide, which is a very simple but very important basic starting material. Next slide, please. In the penicillin area, here we have a transformation where penicillin G is converted by hydrolysis of the phenylacetyl group to the amino, the 6-amino compound, which then serves as a starting material for a range of other penicillin derivatives. Now let's focus first on the chemical transformation is the bottom route. The problem is that if you look to hydrolyze the phenylacetyl group and break that secondary amide bond, there is a problem because you have a tertiary amide in a 4-membered ring, highly reactive because of ring strain. And what you have to do is to hydrolyze one of these amides and don't touch the other one. And so the technique that has to be used in the laboratory is to initially react the benzyl compound with chlorotrimethylsilane and phosphorus pentachloride to generate the iminochloride, the bottom structure. And an iminochloride is much more readily hydrolyzed than an amide. And so this can be hydrolyzed in very mild conditions, minus 40 degrees with normal butanol, and work up at 0 degrees with water. And that gives you the amino compound. Now, using a natural process of biocatalysis, with penicillium acylase in water, 37 degrees, you can do that transformation much more efficiently and simply. And you don't have to worry about byproducts. It's a very clean process. So biocatalysis is increasingly important as a method for organic synthesis. Next, please. Here are some other biocatalytic processes. The direct hydroxylation of picolinic acid to give that hydroxypicolinic acid. Chemically, is exceedingly difficult to do. Here you can do it in one step using oxygen and the biocatalytic process Achromobacter xylosoxidans. In the bottom example, you're converting a terminal methyl group, into a carboxyl group. It's a totally unactivated methyl group, so chemically this is very hard to do, but it can be done very efficiently with Pseudomonas oleovorans in this biocatalytic process. Next slide, please. When it comes to alternative solvents, here it's a matter of designing and utilizing solvents that have the reduced potential for negative effects on the environment. And they serve as alternatives to currently used volatile organic solvents, chlorinated solvents, and solvents that damage the natural environment. The minimization of toxic organic solvents is important with high vapor pressure and reduction in typically large volumes. They're often flammable, explosive, and carcinogenic solvents, so we want to try and avoid those. Phase transfer catalysis is a way of introducing water as one of the crucial solvents, and that's a good thing. But it's even more desirable if you can do reactions in water. Solventless reactions are desirable, but they're limited, although very recent work is developing. I think the solventless reactions are having a bit of a renaissance. There are more useful ways of doing solventless reactions now that are being introduced. Even with solventless reactions, if you're grinding solids together, you still have to use some kind of solvent to get the material out, but you're not using as much solvent as you are in the normal chemical process. The main aspect here for alternative solvents is the use of ionic liquids because of their low volatility. And so they don't have the negative effects that you have with volatile solvents. And the use of supercritical carbon dioxide is important in industrial processes. Again, these are not easy things to work with in the laboratory on small scale synthetic reactions, but they are crucially important in industrial processes. For those of you who drink coffee, the coffee that is soluble, coffee extracts initially were made using chlorinated solvents, and then you have to get the coffee powder. And this was a terrible process, and the coffee at the end was terrible as well. And the Germans discovered that extracting the coffee with supercritical carbon dioxide was much better because it extracted the material without damaging it. It didn't damage the flavor, and you didn't have to get rid of nasty solvents. And so the good instant coffee, and I think all the instant coffee these days, is made using a supercritical carbon dioxide process. Next slide, please. Next slide, please. Here's a very famous, it's an old reaction, but it's a very famous Diels-Alder reaction. This goes back to 2000. It was carried out by Shu Kobayashi and using water to do, have I missed a slide there, or can you just go on to the next slide or go back one? Yeah, this one. The Diels-Alder reaction, we have our diene is the furan, the dienophile is the double bond in the alpha beta unsaturated acid or ketone, whichever you prefer. and a perfectly reasonable Diels-Alder reaction to put together the more complex structure on the right. Now, the Otto and Engberts, when they set out to do this, were interested in seeing if you could do a Diels-Alder reaction in water. And so they were very happy that the reaction proceeded, but they were astonished when they discovered that the reaction proceeded far more readily than it does in hexane, 153 times more rapidly in water. And they hadn't predicted that, and they wouldn't have predicted that, and I don't think anyone else would have predicted that either. But it turns out that the water enforces a hydrophobic environment and enforces some hydrogen bonding interactions that bring the structure together and enhance the Diels-Alder process. Next, please. Now is Kobayashi's water-soluble reaction, which is a Lewis acid catalyzed addition. This is the addition of an enol, a silyl enol ether, to an aldehyde to generate an alcohol. It's catalyzed by ytterbium triflate. And this process, again, the more water you have, the more effective the reaction. And so you have an 80% yield of the product in water. Reaction, again, no nitrogen heterocycles there, but it's a process that can be used again in structures where that is a feature of other nitrogen heterocyclic products as well. Next slide, please. Coming now to the design of safer chemicals, the use of molecular structure design, consideration of principles of toxicity and the mechanism of action. We need to minimize the intrinsic toxicity of the product while maintaining its efficacy of function. And in order to do this, you need to understand the mechanism of action. So again, it's a very important thing to work on control of the reaction, understanding how the reaction works, and that enables you to influence it and control it. It leads you to work out structure-activity relationships, how to eliminate toxic functional groups, and use innovative and ingenious molecular design and generate something which has a harmless or innocuous fate. Next, please. The design of reaction conditions, you want to increase the selectivity of the product and allow the dematerialization of the product separation process. So again, it's this aspect of efficiency. You want high efficiency and high selectivity. And most of the effective examples involve supercritical CO2 or ionic liquids. Next, please. Here are some ionic liquid examples. There's just one example where we have the, it's an imidazolium system, a butyl methylimidazolium hexafluorophosphate. There are a lot of imidazolium ionic liquids. And the first step in the sequence is an alkylation process where it's just a normal base initiated process, but it's done in an ionic liquid. And then you can do the secondary acylation at the indol C3, carrying on in the same flask, same ionic solvent. And this was used in the synthesis of pravadaline, which is indeed a nitrogen heterocyclic compound. Next example, please. Coming to energy, minimizing energy consumption, reduction in mechanical, thermal, and other energy inputs. Intrinsically, it's linked to other green techniques. You want to lower temperatures and as you can do with alternative solvents, and you want catalytic processes that operate with lower energy. Next, please. And so this brings me to the conclusion where if you adopt the principles of green chemistry, what you affect and improve on, you improve the quality of life, you improve environmental protection, you improve human welfare, and you improve sustainable development. You can have those in any order you preference that you wish. I suppose the ultimate is human welfare and quality of life. But that's the basic outcome that you achieve by thinking in terms of these green chemistry processes. So I hope this serves as a background introduction to a broad area of green chemistry, and now the subsequent speakers will deal with much more specific and much more up-to-date material. And I look forward to hearing Professor Hayashi's lecture following as well. Thank you.
Thank you, Professor Black. Do you still have 10 more minutes if you want to present the second presentation?
No, I don't. That's just a bit of spare material. But
okay, that's fine.
I don't think we need that at all.
Thank you very much, Professor.
I think I've used up my time as well.
Okay. Okay, thank you very much for such an amazing lecture. We are now opening the discussion session. So perhaps if you have any question, you may raise your hand and state your question. Or perhaps you can use the chat room instead, and I will relay your question.
Okay, Sastri, could I ask one question for Professor Black?
Yes.
Okay, straight away?
Yes, straight away.
Yes, okay.
Thank you.
Professor Black, we knew that we have a lot of metrics for evaluating the greenness of the reactions, right? From the E factors, atom economy, and then reaction mass efficiency, mass intensity. Actually, when we talk about the greenness of the reactions, which are the best for a chemist when we do something, a reaction like that?
I think these specific terms, atom economy and all these factors, these are minor. I think it's no one really worries too much about them now. They were important to highlight the green aspect, but I think the most important things to look at every process, every chemical synthetic process that you're using, and think about, can I make it cleaner and greener? And the main thing I think really relates to waste material. If you can do your reactions and prevent waste, that would be a major thing. One of my favorite aspects is the photochemical aspect. I think if we can design, I think photochemistry is underutilized.
It is, yes.
It went through a stage where it was popular for some years, and it's not so popular now. It's come back again in photocatalytic processes, a combination of photochemistry in generating catalytic processes. And that's working very well for pure synthesis, laboratory synthesis. I don't think it has been used highly in industrial processes yet. It clearly will be. But as a simple-minded organic chemist, I have a feeling that there are many improved ways that we can use sunlight. And sunlight is relatively indiscriminate, but we can use catalysts that will select specific wavelengths from sunlight And I have a feeling that this is an area that is going to see some development in future years.
Yes.
We don't quite know how to do it yet. But I think if we can get to a stage where we can use something as simple and as sustainable as sunlight, I think that would make a major impact.
Okay. That's thank you very much, Prof. Black. That's why right now I'm doing using the carbon dots. You know, Indriana, a friend of mine, possibly you still remember her. Indriana making the carbon dots, and I'm using it as a catalyst using the UV, using the visible light to conduct the reactions.
Yeah,
I think
yeah.
that's one thing about this. Okay, thanks a lot, Robert.
Good, very good.
Thank you very much, Dr. Tuti, for the question. And now maybe is there any question from the participants? There's a question from Desi Nur Astuti through the chat room. She wants to know if there is any serendipity products or surprising experience, good or bad, that still amaze you during your years of research. Thank you.
Sorry, can you repeat? This is in the chat box or?
Yeah, no, I will just relay it to you. It's okay. So
Yeah.
Desi Nur Astuti wants to know if there is any serendipity product or any surprising experience, good or bad, that still amazed you during your years of research.
Any serendipity, did you say?
Just
Yes,
surprising experience, I think she wants to know.
There's
If-
always serendipity in chemistry. And some of the most important synthetic developments are based on serendipity. It's a very important observation, I think, made by a famous Australian organic chemist, Arthur Birch, of the Birch reduction, and very famous organic chemist. And Birch made a very important statement. The important thing is to be active and keep your eyes open. So you set out to do a reaction and you do that. You think you know what you're doing, you know what you're looking for, and you know what you're trying to do. But you don't always get what you're seeking. But something else happens. And maybe you get a tiny yield of something different that's strange, and you think, oh, this is not what I want. So do I throw it away? No, you don't throw it away. You have a look and you see what it is, and you find something that can be quite different and often is more important than what you're actually looking for. And then you apply your green chemistry processes to make the reaction deliver this other product, the one that you weren't expecting, which is actually more important. So it's a general principle. Don't close your mind to other possibilities, because frequently they will be more important and more innovative. If they are something that you didn't predict, the chances are it's something that nobody else would have predicted either. And so therefore, it's likely to be more spectacular and more important as a discovery. I don't know whether that answers the question, but I hope so.
Okay, thank you, Professor. The participant Desi wants to know that the serendipity product in your own research. She wants to, I think she wants more clarifications on that.
On
your own research history.
Well, my own research has more or less concluded. I am emeritus now, so my own research has been on designing new structures, new molecular structures, heavily nitrogen heterocyclic compounds, heavily indole compounds, and designing new structures that will have new properties and new reactivity. So, for example, we did a lot of work on indoles that had methoxy groups in the benzene ring. And what the methoxy groups do is make these much more active, nucleophilically active than indoles, normal indoles. And not only do they increase the general reactivity, but they change the chemoselectivity, the positions of reaction. And so you can do a whole lot of chemistry that is completely new and generate completely new structures. So you could say this is really molecular architecture and molecular construction. You design a new molecule, new structure, and then you have to find a way to make it. And sometimes you can design a structure that is not easy to make, and you might struggle to make it. And so there's always a compromise between what you would like to make and what you are able to make. And so you develop new structures that are at least achievable.
Okay, thank you very much, Professor. I hope that answers your question, participant Desi. Now I'm going to read off another question from Professor Bambang Purwono. He wants to know, it seems to him that green reaction is very specific reaction. So is there any clue to bring this procedure for general organic synthesis?
Yeah, I think it is a general strategy. It can be applied to any organic synthesis. It's again a mental thing. It's having in your mind when you set out to do something a consideration of all these what you might think of as side effects, peripheral effects, things that you might not automatically think of. But if you have it in mind from the start when you design your reaction scheme, then that's important. And it will often lead you to, it'll save you time if you can build in some of these concepts right at the beginning rather than do a reaction in a very fancy, complicated way and then have to go back and redesign it. I mentioned the process chemists. Process chemists basically throw away the brilliant synthetic design that the research chemists have used, and they start again. And they just think about the practicalities and they completely redesign it. So if you thought about these things before you start, you would save a lot of time.
Okay,
Good
thank you
to talk to you, Bang Bang.
Thank you very much, Professor. I hope that answers your question, Professor Bambang Purwono. Now I'm going to read off another question from participant Muhammad Miharja. So you made the new saline catalyst for with Solihin, similar by Jacobsen, right? Yeah. However, the selectivity is better with Jacobsen catalyst. Would you explain what made your catalyst lost selectivity to a reaction you applied?
Well, it's better because the reactivity is much greater. We're just having a big hailstorm here. Maybe you can hear it. Anyway, hopefully it's all right. The reactivity is greater, and the structure enables us to put in, part of it is having a steric structure that is one enantiomer. And the steric structure has more scope. The indole structures that Solihin developed, that has more scope for variation than the Jacobsen structure. And because of that, we're able to fine-tune it much more. And by fine-tuning it, we can make it well, it turns out to be much more reactive and much more effective in catalyzing the process. But it's too effective. And we ran out of time to redesign it back to get something that is not quite as reactive.
Okay, thank you very much, Professor, for your answer. I hope that answers your question, participant Muhammad Niharja. Maybe just one more question. It's from Ahmad Muhammad Yusuf. He wants to know, since indoles can cause side effects such as skin rashes and diarrhea, how can that be mitigated?
Sorry, side effects in what? I missed the last part. No, I can't hear you.
Sorry, since indoles can cause side effects such as skin rashes and diarrhea, he wants to know how that can be mitigated.
You would need to look at each reaction, the side effects you have in each specific case. I'm not sure whether he's referring to biological side effects or that really you would need to check each specific, you would need to do the testing and check what they are, and when you find out what they are, then you can deal with it. But you have to do the testing first.
All right, I think that's enough for the first lecture of the day. Thank you very much, Professor David Black, for your amazing lecture. Thank you very much for your time and for sharing your knowledge.
Thank you.
Now we are going to move on to our second speaker of the day. Our second speaker is Professor Yujiro Hayashi. He is a professor from Tohoku University, Department of Chemistry, Graduate School of Science, Japan, since 2012. His research interest focuses on organic synthesis, development of new synthetic methods using organocatalysis, and synthesis of biologically active natural products, as he created numerous of publications throughout his journey. Professor Yujiro Hayashi has made so many amazing breakthroughs in the chemistry field with his pod economy organic synthesis. There are so many awards that he received throughout his journey. In 2020, he was awarded with Synthetic Organic Chemistry in Japan. He also obtained the Asian Core Program Lectureship Award for many times. In addition, he received Inoue Prize for Science in 2012. He's currently the editor of Chemistry Letters from the Chemical Society of Japan since 2010. Professor Yujiro Hayashi will be speaking about the pod economy in organic synthetic. Without further ado, let's welcome Professor Yujiro Hayashi. Professor, the time is yours.
Okay, thank you very much, Rasantani, for the kind introduction. First of all, I'd like to thank Professor Laurent and Commeiras and Dr. Marjan for the kind invitation to this very wonderful symposium. And also, I'd like to thank Dr. Black for the excellent talk. I sometimes attended the IUPAC symposium and then attend his lectures. And I'm very happy to be able to talk after his talk. So I'd like to upload my slide. Just wait a minute. Okay. Okay, can you see my slide?
Yes.
Okay, thank you very much.
Yes.
So today I'd like to talk about the photoeconomy in organic synthesis. So okay, wait a minute. I have synthesizing these kind of carbon cycles, and today's topic is green chemistry approaches for efficient synthesis of heterocyclic compounds. I'm not synthesizing the heterocyclic compound, but the information I can give you today is that should be useful for the green chemistry of heterocyclic compounds. So I'm interested in biological compound, and okay, to make a biologically active compounds, we need a multi-step synthesis. So multi-step synthesis is a synthesis from the desired to synthesize the desired molecule from readily available compound by several transformations. In this case, to think about the green chemistry, we have to think not only a single reaction, but also a whole sequence of multi-step synthesis. I will show you one example. This is Tamiflu. I like this Tamiflu. Then as for this compound, I will explain you later in detail. But this is the influenza drug, and then this is a lossless synthesis. And this compound is synthesized from ischemic acid. So this is a multi-step synthesis. And we evaluate the synthesis by a number of steps, in this case 10, or total yield, in this case 20. But today I'd like to emphasize that also time is important. In this case, around 70 hours without purification time. As for Tamiflu is a very important compound, and many researchers synthesize these compounds. So Professor Koris, this is Professor Koris' method. This is Shibata Kanai's method, and this is Fukuyama's method. As you can see, all these cases, more than 10 steps are necessary, and also long reaction time are needed. So thinking about the complexity of this compound, cyclohexane and 3 chiral centers, in this case, this kind of number of steps and reaction time is necessary. And to make these from this Tamiflu, in this case, there is a key step. The key step is as follows. All these cases, key step is the Diels-Alder reactions. In the case of Corey, he used chiral loose acid, boron. And Shibataki's case, chiral barium reagents. And Fukuyama's case, organocatalyst developed by Macmillan. All these cases, catalysis is very important. So to make an important biological active compound or to make a molecules, important thing is catalysis. And also how to combine the reactions. Strategy is also important. So catalysis and strategy are key to hold a multi-step synthesis. First of all, I'd like to talk about the catalysis. So already Professor Black mentioned about the importance of catalysis, and he also mentioned transition metallic catalysis. So already most of you know that transition metallic catalysis is very important, and 20 years ago, Nobel Prize was awarded this field, as you can see here. And second catalysis is enzyme catalysis or biocatalysis. Also, Professor Black mentioned about the importance of this catalysis. So in this catalysis, reaction proceeding in aqueous conditions, high energy safety obtained, and also high specificity is obtained. Third catalysis is organocatalysis. In this case, small organic compound can promote energy selective reactions. In that case, there's no metal waste. In that case, it is environmentally friendly catalyst. And in this case, production is free from contamination matter and exclusion of water and air is not necessary, and most of the ligands are non-toxic. Because of this strong point, organic catalyst has developed rapidly. So I'd like to explain a brief background of organic catalysis. 2000, Professor Des reported chlorine is the effective catalyst for aldol reactions. in these reactions, chlorine is one of the amino acids and it's a safe catalyst, safe molecules. And chlorine react with ketone and generate enamine and aldehyde approaches from the same side from this carboxylic acid moiety because of hydrogen bond activation. That is why we have high energy selectivity and immunoimmune ion forms, and then beta aldol product is generated. So intermediate is this enamine. And 2000, Macmillan reported that LUMO activation method, that is, usually we activate the alpha beta unsaturated carbonyl compounds, we use Lewis acid. But Macmillan proposed amine. In this case, amine reacts with alpha beta unsaturated aldehyde and immunoimmune ion forms. This is a highly electron deficient moiety, so that LUMO of this double bond is lower. So reaction proceeds from this side. In that case, we expect high energy selectivity. And in fact, Macmillan reported this catalyst. It is so-called Macmillan's catalyst, and he obtained high energy selectivity. But as for this specific reaction, as for endo-exoselectivity, there's an issue, which I will explain later. So there are two reaction modes, that is enamine and immunoimmune ions. So this is the background of organocatalysis. So what is the effective asymmetric catalysis? Excellent energy selectivity, high reactivity, easy preparation, wide generality. I hope all of you agree with these four criteria, issues. And each researcher would like to make his or own catalyst. And I'm also one of them. And I like to develop my own catalyst. And in my case, I have developed this catalyst, diphenylpronoside ether. 2005, I reported this catalyst effective aldehyde nitric alkanes molecule reactions. And at the same time, Jorgensen group reported that trifluoromethyl substituted diaryl proinol, which is effective to aldehyde modification of alpha position of aldehyde. So after these two reports, right now, many people like to use this catalyst. This is a safe and secure catalyst. This is prepared for chlorine, and this is inexpensive, and no need to remove oxygen and water, no need for low temperature and high temperature. So this is really practical catalyst. And there are a lot of catalysts have developed, but people like to use my catalyst. The reason is that this catalyst reacts with aldehyde that enamine forms, and that in this case, one of the energy phases is completely sealed. In this case, we can functionalize alpha position of aldehyde. And this catalyst reacts with alpha beta unsaturated aldehyde. In that case, immunoimmune ion forms. In that case, we can functionalize the beta position of aldehyde. In both cases, one of the energy phases is completely shielded, so that we expect high energy selectivity. And there's a lot of reactions involving enamine and immunoimmune ion as intermediate, so that this catalyst can be applicable to many reactions. So these are the compounds we have synthesized using this catalyst. As you can see here, a lot of different structures can be synthesized. So this catalyst has a wide generality and excellent energy selectivity. And we cannot use metal at all. So as for waste, there's no metal generation. So that I think this is one of the green catalysts. So as for heterocyclic compounds, we synthesize these kind of heterocycle, and these heterocycle, and these heterocycles. This catalyst is also effective not only carbocycles, but also heterocycles. So this is one of the examples for green chemistry. So aldehydes, this is the imine precursor and the organocatalyst. No metal, and we can generate important chiral intermediate, and these can convert these kind of products. So this is the real green catalyst. This is another example. This is another example of the green reactions. Professor Black also mentioned that water is a green solvent. And in these are reactions. Some cases, water is very good. In this case, also, water is very great gray solvent, as you can see here. Cinnamaldehyde 2.6 gram and cyclopentadiene around 5 milliliter. This is a 5 equivalent. And my catalyst and add water, no organic solvent, and the reaction proceed room temperature 8 hours. After the reaction, organic phase and water phase are separated, and using decantation, remove water and distill directly. Then we obtain the product, good yield with high energy selectivity. In this case, we obtain exoisomer selectively. Well, in this case, very rare exo selectivity, and also low temperature and high temperature not necessary. And in the green chemistry point of view, in the reaction, we don't use organic solvent. And even in the purification step, we do not use organic solvent at all. So this is no organic solvents, reaction, purification, and no metals. So you can understand that this reaction, this particular reaction, is really green. So I talked about asymmetric organic catalyst like this is really green catalyst. Next, I'd like to talk about combination of the reactions and to make a desired product. That kind of multiplexes I'd like to explain next. So these are compounds I have synthesized so far. And all these compounds has a strong biological activity. That's why I like to make it. Today, I'd like to mention about Tamiflu. So already I show you the structure of Tamiflu. Tamiflu is a real drug for influenza, and many professors synthesize this compound by their own methodology. And this is a real drug. We have to make this compound highly efficient manner. But question is, what is efficiency in organic chemistry? So today's topic, green. Green is very, very important. That is true. And yield is also important. And number of steps is also important. And also cost is important. But today I'd like to talk about the time. Time should be very important too. Then next, my question is, how many days can you make Tamiflu? This question is, when you mix the reagents and how many days afterwards you can get the product? That's the question. For optimization of reactions, it takes a lot of time, sometimes 1 year or 2 years. But this question is after mixing the first reagents and then how many days afterwards you can get the product. So this is our Tamiflu reactions. Two pot synthesis, which I published 2010. Red aldehyde, blue nitroalkane, my catalyst. So this is the micro reactions I have developed 2005. And without isolation, we add these ethyl acrylate derivatives. In that case, micro reaction and Horner-Emmons reaction proceed, and we obtain this product. Without isolation, we add toluene-thiol. In that case, micro reaction of toluene-thiol occurs and isomerization occurs, and we obtain this highly substituted cyclohexane derivatives, good yield, and with excellent enantiomer selectivity. This is a one-pot synthesis. And the rest of the thing we have to do is that conversion of ester moiety to amide by Curtius rearrangement and reduction of nitro group to amine and retromicro reaction of toluene-thiol. These 6 steps also we can do it in one pot, and total 2 pot we can synthesize the Tamiflu. Total yield is 60%. Today I'd like to mention about this particular one pot reactions. This is not this is very complicated reactions, and to explain this, I'd like to explain what reaction is effective for one pot reactions. Okay, What reaction is effective for one-pot operation? In this case, when we do this reaction, we obtain these two compounds. When we like to isolate this proton is acidic. So this is alpha proton aldehyde, and this is alpha proton alkoxy group, so that this proton is acidic and easily epimerized. So if we purify, in that case, diastereotic selectivity reduces. In this case, without isolation, we do next step. In that case, we have a high selectivity. In these cases, we should not do isolation. One pot reaction better. So number one is reaction in which the intermediate compound is unstable. In that case, we should do one pot. And second step is to add to this compound. In this case, when we do this reaction under these conditions, we observe several spots on TLC, and we isolate the spot and determine the structure. In that case, we obtain these three compounds. This is our desired compound 30%. And this is overreaction product. That is, desired compound reacted further with this molecular acceptor because this is very reactive. And in this case, OH and phosphoric ester moiety would be anti, so syn elimination did not occur. We like to convert these two compounds to desired compound, and we saw such conditions. And finally, we found that cesium carbonate ethanol, in this case, these two compounds converted to the desired compound. First reaction is cesium carbonate methylene chloride, and second reaction, cesium carbonate ethanol. The difference is solvent. If we use the first reaction ethanol, in that case, we do not have a good result because ethanol is a nucleophilic solvent, and ethanol did the micro reaction this ethyl acrylate. So that first reaction should be methylene chloride, and second reaction should be ethanol. But we can do this transformation in one pot as follows. First, we do this reaction, methylene chloride, and TLC, there are three spots. After that, we add ethanol. In that case, we obtain the desired product in good yield. So compare the previous reactions. Previous reaction, first reaction, then we have to separate these three using that by column chromatography, using that of solvent. And after that, we add each compound with the same base. And after that, we also isolate, purify it by column chromatography. So compared to this is very simple. Only add the solvent afterwards. So that I think this reaction, this one pot reaction is very important. And we notice the importance of one pot reaction. That is purification economy, chemical waste economy, time economy, and increased yield. So what is reaction is effective one pot operation? That is 2. The side product can convertible into the desired intermediate. In that case, one pot is better. 3, the same reagents, cesium carbonate, are employing subsequent reaction. In that case, we can use the one pot is better. And next, then we obtain this. In this case, R and S, we observe 4:1 ratio. And we need S. So next step is that turn-time molecular addition and epimerization. In this case, this is an equilibration. Even though we purify these two, in solution, it becomes also become equilibration again. In that case, there's no need to purify this. In that case, one pot reacts better. And in this case, also base the same in previous one. So number 4 is reaction in which there is equilibration between intermediate. In that case, we have better to one pot reactions. So what reaction effective one pot reaction? One is I explained reaction in which the intermediate compound is unstable. 2, reaction in which side products generated are convertible into the intermediate compound or final product. Number 3, reaction in which the same reagents are employed in substituting reactions. Number 4, reaction in which there is equilibration between intermediate compound. Number 5, reaction in which the intermediate is hazardous or toxic. Number 5 I not explain, but I hope you all agree with this. So one-pot reaction is really effective to skip the purification. And I think, so the one-pot reaction, green reactions. So green reactions, there are several criteria to judge reactions. So overall yield, average yield per steps, cost of the starting material and reagents, cost of solvents, labor cost, scalability, and in factor, many factors we can judge the reactions. But as for green reaction, we have several terms, that is atom economy and step economy, redox economy. So atom economy, Professor Brack explained this in detail. And I propose pot economy also should be important for green reactions. And also later, I would like to talk about the time economy. I briefly explain about 8 atom and step and redox and pot economy from now on. So already, Professor Brack explained about atom economy, so I don't have to explain in detail. But just look at these 2 reactions. From cyclohexanone to alkanes. In that case, typical reaction, Wittig reaction. But Wittig reaction, in that case, equimolar amount phosphoric phosphine oxide generated. This is high molecular weight molecules. So this is not atom economic at all. But using addition of Grignard and elimination, in that case, byproduct is as follows here. So to design the synthesis, we think about the atom economy, as Professor Brack pointed out. And what is the step economy, which is proposed by Professor Bender? So number of steps is reduced. So in this case, new reaction is very important. So number of reactions reduced, steps reduced. In that case, we can reduce the waste generation. And it is a green method. So one of the examples here, to make cyclotetra-M, octatetra-M, in this case, 100 years ago, 13 steps necessary and yield 1 or 2%. But if new reaction has developed, in that case, these are single reactions and yield is good. So step economy is really important, and for the step economy, importance is new reactions, which is Bender's pointed out. And Baron Hoffman pointed out the redox economy. So multi-step synthesis, in that case, we have a lot of oxidation reduction changes. One example here, ester oxidation state to aldehyde oxidation state. Well, ester is reduced. In this case, usually it's difficult to stop at aldehyde stage because aldehyde, intermediate aldehyde is easily reduced to alcohol. So usually we reduce the alcohol and then oxidize again. Usually this is a 2-step procedure. But if we use wine-leper amide or thioester and using, for instance, this is a Fukuyama's method. In that case, we can make it one step. So in multiplex synthesis, we have a lot of oxidation reductions. So Baron Hoffman pointed out oxidation state should be similar. In that case, number of steps are reduced, and it is economical, and it is a green method. So I would like to mention after the reactions. So everyone do the organic reaction, right? And then after the organic reactions, we have to do tedious post-reaction operations, which consist Quotient reaction, usually add aqueous phase, aqueous solution, we add it, and separation of the organic phase from the water phase, and addition of drying reagents, and filtration of drying reagents, and evaporation of the organic solvents, and then crude material we purify by distillation or recrystallization or column chromatography. Also, these steps, we have a lot of solvents and so on. In many cases, the time after the reaction, longer than the time required for the reactions. And also, this purification after post-reaction operations we use a lot of waste. We generate a lot of waste. So I thought, if we omit the post-reaction operations, in that case, we can reduce waste generation. So that should be green. That is the idea of one-pot reactions. So one-pot economy, that's why I propose one-pot economy. So one-pot economy is that omitting the process of purification and separation of intermediate, reduces the consumption of solvent, reagents, and waste. So that's my idea. But is one-pot reaction is new? So all of you know that this is new. It's not a new idea at all. So 100 years ago, Robinson reported that famous tropinone synthesis. Scusinaldehyde, this calcium salts, amine, so double managed type reaction occurs, and tropinone generated only single step. And this is the famous Johnson's progesterone synthesis. So from these simple compounds and in acid conditions, allyl cation generation, and this kind of cyclization occurs, and complicated structure is synthesized in one pot. This is an excellent method, right? And another example here. This is also a famous example of Hitchcock alcohol synthesis. These linear compounds, treatment KOH, aldol reactions, and amine, and acid. Then other Diels-Alder, other pins from here to here in one pot, one step, one pot, rather complicated alkaloid is synthesized. This is kind of biomimetic synthesis. So nature doing a similar thing, and then Hitchcock developed these reactions following the then this is called biomimetic synthesis. In this case, this is also called a domino reactions. What are domino reactions? So I think most of you know that there's several words: domino reactions, cascade reactions, and tandem reactions. So these concepts, I think, is the same. Similar things remains. Some people like to use domino, some people you like to prefer cascade, but concept are really same. Here the definition of Professor Teach's definition. Domino reaction is a process involving two or more bond-forming transformations which take place under the same reaction conditions without adding additional reagents and catalysts, and in which the subsequent reaction results as a consequence of functionality formed in the previous step. So domino or cascade tandem reactions add all the reagents A, B, C from the beginning, and then several reactions proceed sequentially as expected and obtain the complicated product in one pot. So this is a very effective method, and also this is a green method though. But what's the difference between domino and the one-pot reactions? So one-pot reaction is a strategy to improve the efficiency of a chemical reaction whereby a reactant is subjected to successful chemical reaction, just one reactor. As far as the reaction proceeding, one reaction vessel, in that case, this is the one-pot reaction. And in this case, one-pot reaction covers domino reactions. And one-pot and domino reactions are both a green reaction. Because I said before, then both cases, we skip the tedious operation step, and then waste generation is reduced. But I also point out, is one-pot reaction easy compared to domino reaction? So one-pot reaction, we can add the reagents sequentially, but domino reaction to add ABC from the beginning. In that case, you might think domino is much more complicated, much more difficult, but I don't think so. So one-pot reactions, each reaction step have to proceed in high yield, spot to spot on TLC. Just think about that. 70% is also okay yield, but in 70%, in that case, 30% undesired compound generated. And next step you have to do in the presence of 30% undesired compound. In that case, next step becomes dirty. And the restriction on the amount of reagent. If you use the ratio, excess amount, in that case, next reaction, you have to do the reaction in the presence of excess amount of previous reaction. In that case, next reaction might does not work well. And the restriction on the solvent. If you use high boiling solvent, in that case, you cannot remove high boiling solvent, and high boiling solvent is not good in next step. In that case, next reaction does not proceed. And also restriction on the reaction A plus B and C plus D. And C is desired and D is a byproduct. Sometimes D has a bad effect. So let's think about this reaction. This is a Horner-Emmons reaction. This is a nice reaction to make a double bond, but phosphoric acid is a byproduct. Equimolar amount of phosphoric acid generated. This is a strong acid. So we have to think, we have to choose the reactions which is suitable one-pot reactions. So my point is that one-pot reaction, not a simple combination of each optimized reactions. So as for pot economy one-pot synthesis, then I spent using several slides. I summarized my idea here. So this is my perspective, so that if you have an interest, please read this. I explained the importance of pot economy, and I also discuss about importance and some example of pot reactions. So I told you about 2 pot reactions of Tamiflu. Then after that, I'd like to make the 1 pot, right? Everyone like to 3. Everyone like to 1 is better, right? So I like to make it 1. And I thought this might be difficult, but I finally succeeded. So Dawema and Sylvester and Lou using this nitroalkane with amide here. I use this nitroalkane and same red aldehydes and my catalyst. So same microreaction occurs. And at this ethyl acrylate. So microreaction, Horner-Emmons reaction occurs. And then at toluene, a microreaction occurs and epimerization occurs. And in this case, we already have an amide group here. So next reaction is that at the zinc and nitro group is reduced amine and addition of base. In that case, retromicroreaction toluene occurs and we obtain a Tamiflu. From here to here, it is a 1 pot. And in this case, no evaporation, no solvent exchange. What we do is that we add the reagent sequentially, then you obtain the product. And gram scale, 1 is 28%, not so bad. Then we published this already 7 or 8 years ago. So 1 pot synthesis is possible. And in that case, I told you before, in that case, we can completely reduce the purification step, only last one. And I hope this is one of the green methods to synthesize the Tamiflu. And what I should do next. So I told you about the flow chemistry. So we do the reaction using flask, vessel. So this is a batch system. This is a normal. So all of you do this system. But recently, there's another reaction system called flow. Flow reaction is that at the reagents and in the tube, reaction proceed and obtain the product. In this case, this is a highly reproducible method, and heat generation and heating and cooling is very easy, and also mixing is very easy, very efficient. So there are several strong points of flow chemistry, and also flow chemistry is said to be a green method. Then my method, we do not use solvent exchange. So I like to use my method. I like to apply my method to flow. So this is my 1 pot synthesis. I already explained it. And I like to apply to this flow. In that case, we have a lot of problems. What problem we have is as follows. Problem 1 is that this is not dissolved in organic solvent well. So flow chemistry, everything has to be solved from the beginning. So this is another problem. And cesium carbonate is also solid. And this reaction time is 36 hours. So flow reaction, we have to use tube. Slow reaction, in that case, we have to use a long reaction tube. It's not practical. And this is solid. And also this reaction too slow. So we have a lot of problem. But most critical issue is just this reaction time. So we have to make the reaction faster. So I have a lot of things to do. So before optimization, before application flow, I have to optimize the reaction in batch system again in terms of time. And I will tell you the conclusion. This is our conclusion. In first step, we used another catalyst. Combination of another catalyst is this. So combination of these two catalysts, in that case, reaction fast. And the next reaction is we can use soluble base. And the next reaction we use ammonium fluoride and microwave radiation. So this step, R is major, we need S. Down, we need S. This epimerization is very difficult. So under these conditions, we can epimerize to 1-to-1. Completely epimerize is perfect, but it is impossible for us. 1-to-1 is our maximum. But anyway, 1-to-1, we can do it in 5 minutes. And zinc nitro reduction with zinc is also 5 minutes. So we can do this transformation. Total reaction time is 30 minutes, 20 minutes, immediately, 5 minutes, 5 minutes. So total one hour, I can make this compound. So total is 50%. If we can make in 50%, in that case, we can say such a thing. Okay, after you become sick, then you start synthesize the molecule. Then after 1 year, 1 hour, you obtain the product. I mean, in this case, we have extra time for purification. But first reaction is very important to make the real drug, except in this COVID-19 era. So what about the flow chemistry? We use these apparatus, devices. So we use syringe pump, and so this is a mix. This is connector, and this is a mixture of the solvent. So in this is a small plate, different shape, and here two solution mix well, and the reaction proceed with Teflon tube. And for zinc reduction, we use this cartridge. So these devices, all the laboratory has, and using this system, we can do the flow reaction as follows. So first micro reaction proceed 4.2 meter, 71 minutes. Next, ethyl acrylate. In this reaction, 4 meter, 35 minutes. Then addition of acid. This is 1 meter, 7 minutes. And isomerization. This addition of tetrabutyl ammonium fluoride, 10 meter, 7 minutes. And addition of TMS chloride. And then nitro reduction of zinc. In this case, go to down to up. And we obtain Tamiflu. In this case, total residence time is 5 hours. And total yield is 30%. In this case, we have to replace, change this cartridge every 5 hours. I'm not sure this is really a green method or not. But I would like to point out, only one flow, this multi-step synthesis can be possible right now. And I think this is advancement of science. So I'd like to tell you the one-pot synthesis is very important, and apply one-pot synthesis as a compound. So this is ABT341. This is a drug candidate, and this compound also synthesized one pot using organocatalyst mediated reaction as a key step. And this is a drug called baclofen, and in this case, also we can make baclofen in one pot operations with highly energy selective manner. And this is a prostaglandin ivamethyl ester. In this case, this is a domino reaction, that is Michael and Henry reaction. Then we construct this cyclopentan ring with high energy selective manner, and then total 3 pot, we can synthesize this prostaglandin. And this is a steroid, estradiol methyl ether, which also we can make it using this reaction as a key step. That is also these are domino reactions. So Michael reactions and intramolecular aldo reactions, then we can construct A, C, D ring of steroid in one pot, and estradiol methyl ether synthesized within 5 pot. So the last compound I will explain is the prostaglandins. And prostaglandins is an important compound. These are natural prostaglandins, and these are drugs based on prostaglandins. This is a drug. So many professors call it so good word Noyori Dansevsky synthesized prostaglandins. This is an important compound. And most of the prostaglandins are synthesized by way of chorylactone, and chorylactone is this. And this is chory synthesis of chorylactone, starting with cyclopentadiene, and these are reactions. These are key reactions, and synthesize these compounds. And in this case, total reaction time is 48 hours. So I like to make this compound efficient manner and also green manner. So we developed these reactions. Using my catalyst, I found that ketone and alpha beta unsaturated aldehyde react to 3 or 4 the Michael product in good energy selectivity. So our idea is as follows. When we use this methyl ketone substitute ester moiety, in that case, so aldehyde reacts with catalyst iminium ion forms, and then from methyl ketone, the Michael reaction occurs. In that case, enamine forms. In this case, there would be 2 reaction modes. So 5-member, 6-member. So my interest is which is generated. So we tried this reaction. We found cyclopentanone generated, and also only trans single isomer, and with very high energy selectivity, almost energy pure. So substituted cyclopentanone is obtained, then my target is chorylactone. So chorylactone is this. So this is our retrosynthesis analysis. This OH should be synthesized from this silyl compound by Tamao-Fleming oxidation. And this lactone moiety can be synthesized from this keto ester moiety, reduction of cyclization, lactonization. And this cyclopentanone would be generated from these 2 molecules by my method. That's our idea. And we try these reactions. So first reaction, even though it is silylated, it works pretty well. 10 more % of catalyst 1 hour. We obtain this product nearly enantiomerically pure as a single isomers. And next, we have to reduce this ketone diasterol selectively. In this case, using bulky reducing reagents, we can reduce aldehyde and ketones, and then we obtain this alkoxide. And then treating with alkoxide ammonium chloride solution, then we isolate the alcohol, diol in good yield. Then treatment with acid, lactonization occurs. Then we isolate this compound in good yield. Then we treat this compound HBF4. In that case, phenyl-silyl bond converted to phenyl fluorosilicon bond. In this case, 18 degrees 4 hours. Then carbon silicon bond is oxidatively converted to carbon oxygen bond using H2O2 KF. this 1 hour. So total 5 pot, and total is 58%. We can synthesize this corylactone. I think this is an efficient method. Also, this is already green method though. But I ask my students, please try 1 pot reaction as much as possible. And also, please make it as fast as possible. And my student investigated this reaction in detail, and he found out as follows. So first reaction is the same, 1 hour. The next reaction is THF. Then evaporation and addition of THF, and with the same reducing reagents. And my student found out previously room temperature 1 hour, 60 degrees, the reaction finished only 15 minutes, and diacetyl selectivity does not affected at all. And we obtain this alkoxide. Previously, we add ammonium chloride solution, next HCl solution, and next HBF4. All these procedures are acid. In that case, we can use 1 strong acid. That's our idea, my student's idea. And my student add the same amount of HBF4, that is 10 equivalent here. In that case, 1 minute, this all lithium is protonated, and HBF4 also destroy the remaining reducing reagents, and HBF4 also promote lactonization. So only 1 minute, lactone forms. And then previously, it takes 4 hours, 80 degrees. In this case, we have to change the solvent. And my student found that after the evaporation at 80 degrees, in that case, previous 4 hours, but this reaction finished only 15 minutes, very fast. This is because highly concentrated. So phenyl silicon bond is converted to fluorosilicon bond, only 15 minutes. Then this is acidic reaction conditions. Then we neutralize the reaction. And then after that, we add H2O2KF, the same as the previous. And in that case, the final reaction also proceed well. Then we obtain corylactone. This is 1 pot reactions, and total is 50%. And how about the reaction time? This is 1 hour, 15 minutes, 1 minute, 15 minutes, 1 minute, or 1 hour. So total 152 minutes, we can synthesize this. And previously, we have several operations of tedious post-reaction operations. And in the final product, we have only 1 purification. So definitely, we believe this is a green synthesis. So when we talk about this, we sometimes receive such a question that you do such a lot of reaction. In that case, final product contains a lot of byproducts and so on. Purification would take a lot of time and efforts. Is it really green method? So I will show you the NMR of the final product. This is the corylactone after column chromatography purification. This is the crude mixture before the purification. In this case, some aromatic, so this comes from the catalyst. And as for these regions, so you can see major peak would be corylactone. So crude mixture, crude reaction mixture indicate that crude is really good, not so much byproduct generated. That's why we have a good yield. But why we have such a good yield? Why such a good crude NMR? I'd like to explain this. So this is my reactions. So my reaction first is a CC bond forming reaction to make this. The rest is functional group transformations. So next, rest of the reaction functional group transformations. So first reaction, we make the carbon skeleton. And in this case, catalyst promote 2 roles, that is microreaction and double microreaction. 2 microreactions they promote it, effect very efficiently. And this also catalyst is very green, as I told you before. And total is 50% indicate that this is a 5-step. So total 1 step, 87%. So each reaction proceeds very cleanly, meaning that not so much byproduct. And organic compound, we use para-nitrophenol here. But para-nitrophenol is acid. So final purification by washing acid-base extraction, we can remove this para-nitrophenol easily without color. And except for catalyst, other reagents is inorganic compound. This is inorganic compounds, HBF4 and K2CO3 and H2O2 HKF. All are inorganic compounds, and these inorganic compounds go to water phase after the quench. And we use a little bit excess about this starting material. And this starting material and this reduction stage, it became alcohol, and carbon silicon bond is converted to carbon alcohol bond, and it is this aldehyde, and it goes to water phase. That's the reason the crude NMR is also clean. So even though 5-pot reaction, we do it in 1 pot, but if we choose the good combination of reactions, in that case, reaction simple, crude NMR simple, not so much byproducts, and not generate not so much waste. Once again, I tell you, by thinking about multi-step reactions, we can make a green multi-step reactions. So this is selected a cover picture of Chem-Sci, and if you're interested, please read my articles, my paper. So a guide toward the rapid multiple synthesis of molecule for consideration of reaction method. Number 1 is employ rapid reactions as much as frequently as possible. This is normal, right? And employ reactions that are easy to handle and easy to purify. That's also very important. And employ a domino cascade tandem reaction as much as possible. And in this case, several reactions proceed in 1 pot, in that case, 1 step and 1 pot, in this very efficient method. Also time economical method and green method. And the redox synthesis point of view, design the synthesis based on step economy and redox economy. The number of steps less in that case is green, and this cost it is time effective and also very green. And consideration of optical conditions in the 1 pot. So find the reaction conditions under which the reaction can proceed rapidly. For instance, increase the temperature or concentration. In that case, reaction becomes faster. And also design the synthesis based on pot economy to reduce the number of post operations. In that case, reaction becomes faster to make the reaction rapidly. So I'd like to show you 2 or more 3 slides and then finish it. So is making a molecule short step important? We can save time. Mostly to synthesize a molecule is that we have some other motivation. If sometimes some people have interest in the molecule, biological function, physical properties of molecules. In that case, to make the molecules rapid is very, very important. And unstable compound rapid reaction is really, really important. If slow reaction, during the reaction, compound destroyed, decompose. So rapid reaction is very important in these cases. And PET synthesis, position emission tomography, in that case, fast reaction, rapid reaction have to be must. And in the production process, fast reaction, rapid reaction can save labor cost and save energy cost and save equipment cost. We can use expensive equipment efficiently several times. And I will mention the on-demand synthesis possible. We can make the molecule where we need them. We don't need, there's no need to stockpile the molecules. So this idea of pot economy and time economy, I wrote a perspective recently in Journal of Organic Chemistry. This is the first page of this year. So if you are interested, please read this. I discussed the things, how time economy and pot economy is important. And I would like to emphasize here, in this age of flu-based pandemics, the need for rapid provision of effective therapeutic agents make the importance of time economy particularly clear. So our chemists have to develop a nice drug, nice medicine for COVID-19. In that case, we have to make derivatives. First of all, we have derivatives in short time, many derivatives in short time. And after we choose the candidate molecule, in that case, next we have to make it efficiently in short time, also green method, green manner. So green also important. And chemistry is very important in this COVID-19 time. So in the multiplex synthesis for green chemistry, the catalysis is very, very important. And I believe organic catalyst is one of the green catalysts. And to make a multi-step synthesis strategy is also important. In my case, I like to emphasize the pot reaction is important. In this case, we can omit the purification and suppress the generation waste. And in that sense, this is also green method. And the economy of green chemistry, we have several terms, and we explained, and Prof. Black also explained that atom economy, and step economy, and redox economy. In addition, I'd like to emphasize importance of economy. And also, I think time economy should be important in multi-step synthesis. So JOC's cover picture this year, I wrote this. Previously, time to synthesize 37 hours. And right now, new technologies, in that case, only 60 minutes. The one purification. And co-reductant previous method more than 48 hours. But now, reaction time is only 2.5 hours. So innovation is necessary. In that case, we can make the molecules green and efficient manner. That's the message I'd like to tell you today. So this is my group members. I'm very happy to be very talented students and the hardworking. And this is my last slide. This is our building here. I'm right now 7th floor. So we are in Tokyo, we are Sendai, and Sendai city over there. And we are hillside. Surrounding is a nice green area. Green is very, very important. So this is my last slide. And thank you very much for your kind attention.
Thank you very much, Professor Yujiro Hayashi, for such an amazing lecture. Now we're going to open the discussion session. Probably if any of you have any question, can state them directly or write them in the chat box. Perhaps I'm going to read off a question from the chat box by participant Desi Nur Astuti. She wants to know if that since Tamiflu has some contraindication and serious side effect, such as hallucination, using your catalyst, are the risk of Tamiflu can be minimized?
I cannot follow you. Use which question? Would you say once again the question?
Yes, there's a question from the participant Desi Nur Astuti. She wants to ask if, since Tamiflu has some contraindication and serious side effects such as hallucination, using your catalyst, are the risk of Tamiflu can be minimized?
Oh, this is not the problem, my catalyst. Tamiflu drug itself has some side effects. I'm not familiar with the side effects, but using my catalyst, the final compound is the same. So that synthetic method does not matter of the side effect. And final compound is solid and very high purity Tamiflu can be synthesized. Is it okay?
Yeah, I think that's very clear. I hope that answers your question, participant Desi Nur Astuti. I'm going to read off another question from participant Muhammad Miharja. He wants to know, since pot economy is saving organic chemists times and steps, especially from the purification steps, but one concern about one pot reaction is the functional group formed in product might be affected or labile to the reaction condition or catalyst, which led to the formation of unwanted byproducts. So how can you minimize or prevent this event to occur and get clean product or single pot or two in TLC or the final product?
Well, thank you very much for the question.
Yes.
One pot reaction, as you mentioned, as I explained in the middle of my talk, that we have to do that as the number of steps increases. So reaction mix like a dirty. Lot of side product or byproduct and also some of the unreactive starting material remains, reagent remains. In that case, reaction becomes difficult to proceed. So in that case, we know, okay, we re-optimize once again what the side product affect whether the side product affect the reaction or not, and optimize a little bit more. So optimization is a bit different. Mostly, first we optimize the reaction using pure compounds. And next, we think addition of previous reactions or side product, and then also optimize once again. So more optimization necessary. But in that case, we can skip the purification step. In that case, it is very effective. And I think it's green. Is okay?
Yes, I hope that answers your question, participant Muhammad Miharja. Now I'm going to read off another question, perhaps from participant YUS Putro. Your catalyst seems powerful for various organic reactions. Does your catalyst proceed homogeneously? How do you separate your catalyst from the reaction system? Is your catalyst now commercially available? Thank you.
Okay, catalyst is commercially available. So the catalyst separation, catalyst comes, this is amine, and have a bulky phenyl group. So even though catalyst under the acid conditions make salt, it does not go to water phase. It comes to organic phase. So usually we separate it by column chromatography. And it's not so difficult. Also, it depends on the desired compounds, polarity of desired compound, the catalyst polarity. But we do not have so much difficulty to separate it. Please use it if you have a chance. It's okay?
Yes, thank you very much for the answer, Professor. Is there any other question from the participants, perhaps? You can use the chat box or you can state them directly.
I think for me.
Oh, okay. Please. Bye-bye.
Okay. Thank you, Professor Hayashi, for the outstanding presentation. Yeah. So actually, the lab where I did my doctoral study is the user of your catalyst.
Oh, thank you very much. Thank you.
I also try your catalyst several times for our reaction, but however didn't work.
Wow, very sad.
Yeah.
But if you ask me, in that case, I can give you some advice.
It was long time ago. So it is interesting, yeah, when you can reduce the reaction time here, for example, for the synthesis of correlactone. But could you please give how do you say, a comment here? How could you reduce your reaction time while maintaining the stereoselectivity?
Your question is, would you say once again?
Yeah, how could you reduce the reaction time while maintaining the stereoselectivity in the synthesis?
Okay, okay. First reaction, we cannot speed up. Okay, I show you this. This is if we use 10 mole% catalyst 1 hour and 5 mole% 8 hours, the yield is really same. The yield is really same. So in this step, we cannot speed up. Oh, 1 hour should be okay, 10 more percent okay. In this case, we use 10 more percent and 1 hour. And other reactions, this is we are happy. Usually we do the reaction lower temperature to in this case, diacetyl selectivity of the reduction is important. So students did it the normal condition that around room temperature, and it works. And I asked my student to speed up the reactions. And the student found that, oh, even though 60 degrees, diacetyl selectivity data reduced. Much higher in that case, diacetyl selectivity reduces. And this is one of the success of short reaction time. This I did not expect it. Usually, this kind of silicon phenyl bond conversion take a lot of time at higher temperature. But my students found that we have to change the reaction solvent so that he removed the solvent a little bit higher temperature. Usually, we remove the remove the solvent at room temperature, but next step is a high temperature. He evaporates the solvent at higher temperature, during which this reaction occurs. So this is kind of unexpected for us. So those small discoveries, this treatment, ammonium chloride and HCl treatment, this we expected that this can be replaced by HBA4. This we expected. But first we have to do one by one and check the yield and stereochemistry and structure.
Yes.
Then when we combine, we do several things and then make it faster. So we recognize that to make the reaction faster, I told in the middle of my talk that one is to increase the temperature. Sometimes side reaction occurs or selectivity decreases, but sometimes it might be okay. And second, concentrated conditions, reaction is accelerated. That is a normal thing. But sometimes side reaction occurs. And also we check the solvent. According to solvent, reaction speed is different. Of course, according to solvent, not only reaction speed, the yield is also different. So several parameters we change it and choose the best one. And in this case, we choose it based on time economy, not yield. Based on both time and yield. So most people optimize the reaction yield, right? So we take a balance of yield and speed and so on. So that's what we did in this screen here. So it is answer to you?
Yes, thank you.
Thank you, Dr. Idham, for the question, and thank you, Professor, for the answer. Perhaps just one more question from participant Muhammad Gadjah. He wants to ask about, for the Tamiflu, did you run the reaction in gram scale, or have you ever scaling it up large with the same reaction time, 60 minutes?
Okay. All the reactions we try. Wow, I'm sorry. Okay, 60 minutes synthesis. Also, we try 1 gram. All the reactions we try 1 gram. First, we try 100 milligram scale, but this reaction, okay, I have to mention that. Microwave conditions, these conditions, 60 minutes conditions, we try are much small scale because our group have a microwave. In that case, apparatus is about 10 milliliter. So 10 milliliter scale, we do it. In that case, Tamiflu is obtained, I forget about that, 100 milligrams, 700 milligrams, 100 milligrams, so on, I forget about that. Then, without microwave, normal heating, oil bath heating. In this case, this is about 2 hours. Oil bath heating, in that case, gram scale synthesis, 2 hours we can make this. So microwave, in that case, much faster. So 1 gram scale is also possible. And is okay. And scale up is okay in this case. Organocatalytic reactions, as I told you before, we don't have to so much careful about the content of water and also content of oxygen. In that case, I will tell you, organometallic chemistry, some of the organometallic chemistry, we have to use a very nice water dry solvent to completely remove oxygen. And then we have a best yield, sometimes. But in these cases, this reaction, small amount of water okay, and oxygen okay. And other reactions same, not strictly rigorous of water and oxygen. And then scale up is easy. That's my answer. And also that's a good point of organocatalysis.
Thank you very much, Professor. Such an interesting and amazing lecture.
Yeah.
I think that's all for the second lecture of the day. Thank you very much, Professor Yujiro Hayashi, for your time and for sharing your knowledge to us. Thank you very much. Arigatou gozaimasu.
Thank you very much.
Okay. Sorry. With the end of Professor Yujiro Hayashi's presentation has marked the end of today's lecture. It has been a pleasure to be your moderator of the day. I hope that after this lecture, we can contribute to the chemistry field in a much greener approach. Perhaps I would like to invite Professor Commeiras to give a few comments on today's event. Professor Commeiras?
Thank you very much. So just curious to conclude, thank you very much for the speaker, Dr. Professor Black and Professor Hayashi. It was very wonderful lecture for us, and we learned a lot about your own works. So through your presentation, you can see that green chemistry is very important, and you have to think about, to take care about our planet for the next future and for our next generation. So I hope that everybody enjoy this conference, and I will say see you in the next time. I don't remember exactly the date for the next conference. So thank you, Nature, thank you, Idham, for today.
Okay. Thank you very much, Professor, for your comments on today's event. So now I'm going to pass the control of today's event back to the host of World Class Professor 2021. So Dr. Idham Darussalam, the time is yours. Thank you very much, everybody.
Okay, thank you very much, Safi, to moderate this session. Yeah, it was very interesting lecture. So as the closing speech, yeah, again, I would like to thank you for Professor Black and also Professor Hayashi for the interesting presentation. Yeah, well, it encouraged us, especially in the field of organic synthesis, yeah, to elaborate, to develop here the organic synthesis. Yeah, so for information, yeah, so the next guest lecture will be held on the 29th October 2021. Yeah, so we'll have 3 lecturers. Yeah, the first one is Professor Melati Herudin from Universitas of Malaysia. And then we have Professor Rawat from University of Delhi, India. And we have Professor Patel from Sardar Patel University in India. Yeah, so you can find the link of registration in here. Yeah, so as in the presentation of Professor Black, yeah, he talked about the ionic liquid, yeah, as the clean solvent here in the organic synthesis. So if you'd like to know more about the ionic liquid, yeah, just follow the guest lecture. Besides, we also talk about the application here, about the heterocyclic compound here, particularly in the pharmaceutical application. So don't miss it. Yeah. So see you again in the next guest lecture, again at 29 October 2021. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon.
Thank you. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh. Okay, now perhaps this is the closing.
Yes.
You may leave the meeting now. Yeah.
Yeah.
Okay. Thank you very much, everybody.
Thank you very much.
See you on October 29th.
Yes. So excuse me to the participant. Yeah, please fill the feedback. Yeah, you can find the feedback link on the chat. Yeah, thank you very much. Thank you, Safi.
Okay, thank you very much, Marjan, and also thank you very much, Professor Commeiras. I'm very happy to be able to join today's seminar, today's symposium.
Thank you
Really,
very
thank
much.
you very much for invitation.
Yeah.
And I don't know that you use Biocatalyst.
Yeah. Yeah, the lab in France, yeah, they use a lot of the catalyst, organic catalyst developed by you.
But again,
Jean Rodriguez of Marseille.
Yes.
He's a very an expert in organocatalysis, and he uses your catalyst to do its transformation. So, your catalyst is well known in our laboratory.
but anyway, it's my great pleasure to have a talk in to your university students. Even though COVID-19 might be possible, otherwise
Yes.
it cannot be possible, I think. Okay, Professor Black is already left here. He left.
Professor Black.
He left, right? Okay.
I think yes.
I'd like to say hello to him, but anyway, but next time if I have a chance, I'm going to talk with him. Okay, so
Yeah.
really thank you very much, and I really enjoyed today's today's symposium, and I hope the rest of the symposium will be also successful.
Thank you very much.
Yeah, goodbye. Bye-bye.
Goodbye. Ciao. Ok, merci beaucoup, Laurent.
Ça va?
Ça va.
Yeah.
Oui, la semaine.
Je sais pas que je fasse une petite conclusion. Donc,
ouais.
La prochaine fois, je fais aussi un discours d'entrée, mais parce que je ne sais pas trop ce que tu veux que je dise, c'est-à-dire de discours. Il faut que je parle un petit peu des speakers ou quoi, pour le mot d'introduction pour la prochaine fois.
Bah, tu peux le faire comme ça si tu veux. Ouais.
Je ne sais pas trop en fait ce qu'il faut dire, je ne sais pas trop.
Ouais. C'est un peu le bio quoi pour la semaine prochaine.
Ok.
Ouais.
Parfait. Parfait. Peut-être pour mes conférences,
ouais.
On changera peut-être les titres, on inversera. Je pense que je vais parler des lactones en premier, puis après je parle de bon, c'est pas très grave. Voilà.
D'accord. Oui.
Si les gens suivent cette conférence, ça sera peut-être plus simple de parler comme ça.
Ok, on fait comme ça. Donc tu peux m'envoyer le titre. Ouais,
ou alors on pourra le faire on pourra en faire en 2 fois, partie 1 et partie 2, toi peut-être, puis
ouais.
On fera peut-être partie 1, partie 2, on fera un titre avec partie 1, partie 2. Comme ça, je peux parler de tout quand je veux. Ah, okay. Je ferai ça. Okay, ça.
D'accord, ça marche. Ok.
Bien. Bon, la modérateur, c'est bien. Hein?
Ouais.
Vous avez de la chance, hein?
Ouais, c'est pour ça. Je l'ai choisi.
T'as choisi, hein. T'as bien fait, t'as bien fait. Ok,
D'accord.
ok.
Oui, je te laisse.
Allez.
D'accord. Allez, ciao. Merci.